Example 8.10. Two blocks are connected by a light string that passes over a frictionless pulley. So here we have a pulley with a frictionless and massless. Okay, in this case, if we have here T1 and here we have T2, T1, T1, T2, and T2, in this case, you can say T1 equals to T2. Okay, it's very important. Okay, we continue. The block of mass M1 lies to a horizontal surface. We have M1 on the table and is connected to a spring of K constant, as we see here. The system is released from rest when the spring is unstretched. So when the spring is at equilibrium at x equals to O, I release the system without initial velocity. So initially, M1 and M2 don't have velocity, and the spring is without any elongation, x equals to O. This is the initial state. If the mass M2 falls a distance h before coming to rest, calculate the coefficient of kinetic friction mu between the block of mass M1 and the surface. We have to calculate the value of mu. Okay? Let me okay. Before we have to put the reference of each block, because here we have two dimension. When we have two dimension, you put xy for M1 and xy for M2. Don't take one xy axis for the two objects. So here we choose a reference for each block. Okay, you have M1 between initial position and final position. Let's say we have x and y. This is the origin here. So as you see here, we don't have a changement of the height. In this case, we have the gravitational potential energy, initial and final, of M1 equals to 0. Okay? Let's take M2. M2 moves from this point to this point. So here we have the highest point and the lowest point. In this case, you take the lowest point as a reference, okay? You take x-axis at this point. Okay, now it's clear about the reference. Now I come back to continue. Here we have a tension T. Here also T and T. Okay, we have M1. Initially, let's take this position of M1, M2, because I take a system. When I talking about the mechanical energy, initial and final, I take the all system. When the system was at this situation here, okay, M1 and M2, this is the system A. System A. Okay, I'm talking about this situation. In general, you know, we can say delta mechanical energy equals to delta kinetic plus delta potential equals to omega F. You know, in this system we have F. We have interaction between the block M1 and the plane. So you have to put this relation. Before, let me explain here. M1, when M1 moves to the right, M2 will move down. Here we have non-elastic string. So V1 equals to V2. Okay. When M2 moves a distance h down, is a maximum distance. When I say maximum, it means here we have a maximum elongation of the spring. We can say we have X maximum as a final state. And M1 will move also a distance h to the right. Here we have h. Okay? The same distance because it's inelastic string between them. Okay, this is the initial state. In this initial state, we have M1 is here, we have K without elongation, and we have M2 is here. Let me take the state A. In this state, we have to calculate the total kinetic energy of this state. We have to calculate the total potential energy G of this state, and we calculate the total elastic potential energy of the state A, excuse me, of the state A. We can say state initial also. Let me say here we have the initial state. Here we can I, and I. Okay. Initially, what we have? We have M1 is at rest, M2 is at rest, and also we have the spring is at rest. So we don't have any kinetic energy. About the gravitational potential energy, we take independently M1 and M2. M1 initially and finally, we don't have for M1 any height. So we don't have for M1 potential energy, G. 0 for M1. Plus, for M2. M2 initially has a height h with respect to the x-axis here. Here we have x-axis. And we have a height h. I said we have to choose the lowest point between the initial position and the final position as x-axis. So we can say here we have M2 G times H. This is about the initial gravitational potential energy. Now about the elastic. we have only one spring. For the spring, we don't have x at this point. X equals to O. So we don't have half kx squared. Now the system moves to the right. Now I take the final, here we have initial, okay? Initial. Now I take the final state. The final state, the object M1 moves to the right, here, and let me delete this one, and let's take the spring like this. Okay, it's not perfect, it's okay. And this one we don't have in the final state, it will be down. Okay, perfect. Okay, this is the state final. In the state final, what we have? First of all, we have elongation, we have expansion of the spring, we have x. Okay, is the final position. You know, x equals to h. X equals to h, because I said we have the final position, the object M2 moves h. And you know here, if M2 moves h, M1 also will move h. In this case, x equals to h. We can say here like this. Okay. H between the initial like this. Oops. Okay. Okay. About the kinetic, you know, at the end, M1 and M2 will be stopped. Okay, because at the maximum expansion, we don't have motion. So here, we don't have kinetic energy final, we don't have velocity. Now about the potential, gravitational potential energy of 1 and 2 as a final situation. In this situation, we don't have height for M1. H equals to O. So no for M1. For M2 also, at this position, H equals to O, because the object is at the x-axis. We don't have H. Here we have x-axis. So in general, we don't have PEG final. About the elastic potential energy final. Yes, we have x. We have x, so we have x squared. In this case, x equals to h, we can say have kh squared. Okay, this is about these values. We have here omega f. We can say omega f equals to minus, because it's opposite to the displacement. Okay, here we can say we have a displacement from here to here, and F is opposite to the displacement. It's opposite. Here we have F, opposite. So omega F equals to minus F times the displacement. Okay? We can say minus F mu times N times the displacement. The displacement is from here to here. This value also equals to h. dx equals to h. So we can say h. Okay, we substitute the value of omega f, of delta kinetic energy, of delta potential energy, and we calculate the value of mu. Let's say here we take equation 1, this one. What we have, delta kinetic energy. We have delta kinetic energy equals to kinetic energy final minus kinetic energy initial plus potential. I have to take PEG and PEE, okay? Two potential energy. Here we have PEG final minus PEG initial plus PEE final minus PEE initial. Okay? Equals to, you can say here, equals to this value. Okay? We substitute each value here, equals kinetic energy final equals to O. Kinetic energy initial equals to O. This one and this one. Plus potential energy G final and initial. Final equals to O. Initial equals to M2GH. Elastic potential final equals to K over 2 H square, and initial equals to O. All this equals to minus mu times N times H. Okay, let me clean here. N, we can calculate N from the Y component of M1, okay? Because we have a friction only on the block M1. So N is up, mg is down, equals to O, because we don't have motion along y-axis of M1. So N equals to M1g. So minus mu, I have to calculate it, times N equals to M1. M1, I think we have its value. I have to calculate it in function of, in terms of. Here we have M1g as N times H equals to minus m2 gh plus k over 2h square. Okay, we can eliminate h and 2. We get mu equals, we can put this value to the right and this one to the left. We get here m2 g minus k h over 2 divided by m1g. This is the value of mu. Okay, first of all, the most important point here is you have to take a for each object x and y independent. Okay, m1 has xy and m2 has xy different. Okay, don't take same xy for the system, all the system. Second, here you have to know you can use in all these exercises, you can use delta mechanical energy equals to the delta kinetic plus delta potential equals to omega f. If you have F equals to O, in this case, you have a conservation of mechanical energy. If we have F, you have to calculate it. This is part part A. I think we have part B. Let me see. No, we have only one part. It's all.